Okay, again the microphone is active, so we go back to our exercise session as we established before. So our exercise session is as usual very alive, very important for you, and I suggest you to follow it in a very active way. So now we keep on considering the problem of establishing conservativity of fields. And so the which fields, now we go to three-dimensional fields. So again, the question we are treating, and it is always the same. So we want to establish, whether the field the field here is f equal to e to the y I plus x e to the y j plus z plus e to the z k is conservative, and if so, if it is conservative, then compute a potential. So exactly as before, so let me try to solve this exercise, and again we look for irrotationality. So first we check the irrotationality of the field, which is, as you know, a necessary but not sufficient condition. So the irrotationality of the field, which means first compute the first component of the curl, which is dy f3 minus dz f2. So dy of f3, which is 0, minus dz f2, which is 0, 2. So the first component is 0. So the second is dz f1 minus dx f3. So dz f1 minus dx f3, f1 is this guy here, which is 0, and dx f3 is 0. So also the second is 0. So let us go to the third component of the curl. So we have dx f2 minus dy f1. So dx f2 is e to the y, minus dy f1 is e to the y2. So this is equal to 0. Then we have that the curl of f, so nabla cross f, is equal to 0. The field is irrotational. I stress again, with respect to previous exercise where the field was planar, the new thing that we have here is that we have to check three things, the three components of the curl. Okay? Just the three components of the curl instead of one. But then if all of these three components are equal to 0, then we have irrotationality. And remember that irrotational does not mean conservative, but we are almost there. Okay? Irrotational is a necessary but not sufficient continuous condition. In order to make it, in order to have the conservativity, we have to check the domain of F. But again, the domain of F is R3. We are in the space, the domain is R3 because the components are functions which are defined in R3. There are very simple polynomials and exponential of components. And R3 is simply connected. Then we have that F is conservative. Okay, so since F is conservative, we can find a potential. And again, we use the same computation we used before. So we have the three axes, x, y, z. We want to compute the field at a point x, y, z to compute the potential. So in order to find this potential, we fix a 0 of the potential. As usual, we can fix it at the origin, and then go up to the field through a simple path. Of course, here you can do whatever you want. You can just notice here that when x is equal to 0, the second component is 0, so perhaps it can be smart this time to follow this line. First of all, let me here consider x, y, 0. So as a first step, you can go from 0 up to here to 0, y, 0, and this will be our gamma 1. Gamma 2, let me change color, will be here. Gamma 2 up to x, y, 0, and then with gamma 3 we get the point of our interest here. So this is the path I suggest you, but it is not the only choice. It is quite a simple path. The iPad is becoming crazy. By my drawing, it seems to be self-crossing here at this point, but this is not true. It's a matter of perspective. Okay, here we are behind morally, and here we are forward. Okay, so here we have the computation, which is f scalar dr on gamma, where gamma is the union of gamma 1, gamma 2, and gamma 3. So we have that this is equal to the line integral of f on gamma 1 plus the line integral of f on gamma 2 plus the line integral of f on gamma 3. Good. Then gamma 1 is what? Gamma 1 is 0 t 0 with t moving between 0 and y. gamma 2 is t y 0 with t between 0 and x, and gamma 3 will be x, y, t with t in the interval 0, z. So R1 dot, so when we are on gamma 1, the velocity is 0, 1, 0. On gamma 2, it will be 1, 0, 0. We have to differentiate with respect to the variable t. And on gamma 3, it will be 0, 0, 1. So let us consider the first of these integrals, these three integrals, the integral on gamma 1, which is f dot dr. So on gamma 1 we have only the second component that survives after the scalar product, so because 0, 1, 0 is the velocity, and the second component of f is x e to the y, but x is always equal to 0, so this is 0. This is why I chose this path, starting by moving on the y-axis and not on the x-axis. But it is the same, it is just a matter of having just a bit more comfortable computation, but this is really nothing so important. And on gamma 2, you have f dot dr, f dot dr. So on gamma 2 it is the x component surviving because the velocity here is 1, 0, 0. Then on gamma 2 we have e to the y. It is the integral between 0 and x of e to the y in dt. Here you have to pay attention to the variables, because here we are integrating on t, and here we have e to the y, because this is the first component, only e to the y. So e to the y is a constant in this integral. So the result will be x e to the y. Okay? And in gamma 3, only the z component is relevant, and this will be the integral between 0 and z. Here z is equal to t, and we have t plus e to the t. In dt. So it is clear that here we have t squared over 2 plus e to the t to be evaluated between 0 and z. So you have z squared over 2 plus e to the z minus, here we have a 0 and here we have a 1, so minus 1. So our potential will be u x y z is equal to x e to the y plus z squared over 2 plus e to the z minus 1. And so let us verify that this is the true potential. So we have du dx is equal to e to the y, which is exactly the first component, f1. Then du dy is equal to x e to the y, which is f2, and du d3, sorry, dz, is equal to z plus e to the z, which is the f3. So u is a potential, but perhaps, as some of you could have noticed, we can simplify the expression of this potential, because here there is -1, which is a constant. This -1 just disappears when we find the field again through differentiation, because it is a constant, so it does not count at all. So one can get rid of the constant -1 and end up with a shorter expression for the potential, which is u, let me call it u tilde, just to use another symbol, of x, y, z equal to x e to the y plus z square over 2 plus e to the z. Okay? Of course, this expression is correct. It has nothing worse than this. This is just shorter. You spare writing -1, so you are more ecological, which is always very important. So I leave you some exercise as a homework. I will not correct it, but as a homework, so establish same questions, so whether it is conservative, and if so, find a potential. So same questions for the three-dimensional fields. So you have f equal to 2x y sine of z I plus x squared sine of z j plus x squared y cos z k. So same questions for this field, or this is the first. Second, f equal to logarithm of xi plus logarithm of yj plus logarithm of zk. Be careful with the domain. It is not R3, of course. And so again, 3f is equal to e to the x sine of y I plus e to x again, cosine of z j plus z cube k. Fourth, f equal to xy squared I plus zy squared j plus y z squared k. Okay? So please fight against these fields, and the strategy is always the same. So the method is First, compute curl F. Okay, if curl F different from 0, then F cannot be conservative. It's not irrotational, so it's not conservative. In order not to be 0, it is sufficient that one component is not 0. The other one can be 0. It can have two components equal to 0 and the third one not 0. So it is not conservative. Okay? Second, if the curl is equal to 0, then verify whether the domain is simply connected. First, so second, if the domain is simply connected, then F is conservative and you may compute a potential. If it is not, then the case is more delicate, especially if it is three-dimensional. I don't want to give general rules on that, because really you have to go around the holes. It depends on how many holes you have. If it is three-dimensional, it is quite complicated. So, however, I don't know whether if we will have time, we will treat some example. But in general, here there is no a clear and simple recipe. Okay. With this, I will stop with Green's theorem and conservativity. I would like to go towards other two theorems, which are divergence theorem and Stokes theorem, so-called also curl theorem. And so providing you with these nice tools that help you in analyzing also physical situations like in electromagnetism. So I want to really to convey the message that what we are doing here is quite abstract, quite mathematical, but this is really what is needed to understand electromagnetic fields, for instance. So it is important also for non-mathematicians. Okay? See you next time.